Okay, so here you can see the principal quantum number now spread across the x-axis. Okay, so notice that we're doing that. So this is sort of reorganizing the information on the previous slide a little differently to show that if our principal quantum number is 1, there is only one set of atomic orbitals there. If the principal quantum number is 2, we can see two sets of orbitals there, an s and a p type. Note that in the p orbitals, we knew that there was a p x, a p y, and a p z, and that these are degenerate. They all are co-located on the same energy level. Okay, so all reflected on that same red line. And in the 1s and in the 2s, there's only one type each there. When we go to the third principal quantum number, we have a similar situation. We have a 3s and a 3p with three types of p orbitals, px, py, and pz. And now we have our 3d orbitals that are available. Okay, and recall there we expected 5, so 5 d orbitals. I'll just divide this blue line into 5 segments. 1, 2, 3, 4, 5. So there are 5 segments there. And the pattern kind of continues. In the f orbitals generated for principal quantum number 4, we'll see actually 7 f orbitals generated there. Okay, so how do we predict the format of the order in which those orbitals occur on that energy scale? Recall, this is an important order because electrons will locate themselves in the lowest energy configuration first in an unexcited atom that is in matter. Okay, so in the case of carbon, with its 6 electrons for the neutral carbon atom, we would put 2 electrons into the 1s orbital, another 2 electrons into the 2s orbital, and the final 2 electrons distributed into 2 of the 3p orbitals shown here. So you can see here, knowing the order in which to fill up these options is important. The number 6, of course, came because we knew that there were 6 electrons to neutralize the 6 protons in the carbon atom, and that carbon was the 6th element in the periodic table. Okay, so here's a periodic table with some information imposed over top of it to help us note the order. So note that we're in the first row here, here's the second row, and here's the third row, etc. And to help predict the electron configuration, to help us predict where the electrons are located, we can walk across the periodic table. So if we needed to define the electron configuration for helium, we know that helium is the second element in the periodic table. And so if I'm going to handle a neutral helium atom, I need to describe a total of 2 electrons. So you can see here that we're going to use the 1s orbital, and we said that we could put up to 2 electrons in that. And so the 1s orbital is going to have 2 electrons in it. So the superscript 2 in the electron configuration here indicates that there are 2 electrons present in the 1s orbital. Okay, let me just clean that up and we'll try another one here. Okay, handling something like silicon now. Silicon is the 10, 11, 12, 13, 14th element. So silicon is the 14th element in the periodic table. So our total number of exponents in the electron configuration should total 14 if we're handling a neutral silicon atom. So to predict the electron configuration for silicon, we can see that it's going to be 1s, 1, 2 to get us to that point. So 1s2, okay. We've kind of built the electron configuration to be identical to helium thus far. Next, we have to use the 2s orbitals to walk across the first two columns. So we're going to use a 2s2. We've now used a total of 4 of the 14 electrons that we need for the silicon atom. Our next block is the 2p block and the set of orbitals there, so 2p. And we're going to go across all 6 of those. So 2p, 1, 2, 3, 4, 5, 6, 2p6. We've got a total of 10 electrons so far, where electron configuration is equivalent to neon at this point. We need to keep going, so we're now going to go to the 3s. And again, the 3s can accommodate 2 electrons at max, and so that's what we've got there. We're now at 12, and 2 more to go, so we need to get now into the 3p orbitals, and it looks like to finish off silicon, we're going to have 2 electrons there. Okay, so that would be the electron configuration for a neutral silicon atom. In some experiments, you can actually ionize or remove or react away an electron from silicon. So if we were able to react away 2 electrons from silicon, we would need to ask the question, where would they come from? From which orbital would we remove 2 electrons if we're to ionize silicon? And so in the electron configuration, as we walk left to right, energy is increasing. And this helps us predict where the 2 electrons would come from. So we would expect the 3p electrons to be most easily removed. So in a certain reaction, if 2 electrons were to remove themselves from silicon, it would be these 2 electrons that would remove. And so a silicon 2+, if possible, would have an electron configuration of 1s2, 2s2, 2p6, 3s2, and then empty p orbitals given the reaction. Okay. A couple of notes is you can use the this approach to generate the electron configuration for most things. So once you move into elements in the 4th row, everything is still fine. Notice that the 3d orbitals are in the 4th row, and the 4d orbitals are in the 5th row, and that there is no 2d or 1d orbitals in the periodic table, and likewise for the p, there is no 1p orbital in the periodic table. Okay, and again, this is all very good because it helps us understand where the most reactive electrons are and what that might mean for matter in material science and engineering.